That means in this mechanism, the oxygen will act as a nucleophile. It will attack the less substituted carbon number 5 and open up the epoxide, putting a new lone pair of electrons onto the oxygen. Hey, Chem Ninjas. In this video, I'd like to talk about the epoxide opening reaction under basic conditions. There are separate mechanisms for when an epoxide is opened under basic conditions and under acidic conditions, and I'll have a separate video about epoxide opening under acidic conditions that I'll link to down below. When I look at the setup, I know that this is epoxide opening under basic conditions because my reagent, sodium methoxide, is a strong nucleophile and strong base. This isn't a video about categorizing nucleophiles and bases, but if you want to watch that video, I have that linked down below as well. That means the oxygen will be the nucleophile, which means the epoxide will be the electrophile. The question is where? There are two carbons of the epoxide that could be attacked by the nucleophile to do this epoxide opening reaction. The fact that we're doing this reaction under basic conditions is going to be the key to helping us figure out where the epoxide reacts. That's why it's important to be able to recognize this reagent as a base and this reaction is under basic conditions. So what do I know about strong nucleophiles, strong bases like sodium methoxide? Where have I seen them before? I've seen them before in SN2 reactions. This isn't a video about SN2 reactions. I have a link to that video down below. But when I think about an SN2 reaction, SN2 nucleophiles are strong nucleophiles. They directly attack electrophiles. They do concerted reactions. They have enough inherent energy to do the thing they need to do. But in an SN2 reaction, even the strongest nucleophile can't react with all types of electrophiles. Sterically hindered electrophiles can't do SN2 reactions. In fact, tertiary electrophiles don't do SN2 reactions at all. Again, that's in the video I've got linked down below. So when I look at this base and I look to see where the epoxide will react, it will react at the less substituted side of the epoxide for steric reasons. Think SN2. The nucleophile will react at the less substituted side, not the more sterically hindered side, for steric reasons. So with that in mind, for strong nucleophile, strong base, epoxide opening under basic conditions, think SN2, where the nucleophile will attack the less substituted side. That means in this mechanism, the oxygen will act as a nucleophile. It will attack the less substituted carbon number 5 and open up the epoxide, putting a new lone pair of electrons onto the oxygen. That's going to form an intermediate with an oxygen with a full negative charge on carbon number 6, and the new methoxy group will be attached to carbon number 5, at least as I numbered it in this molecule. To do this, we kicked out a leaving group that's O-. O- is not a very good leaving group. I have a separate video on leaving groups that I'll link to down below. O- is not a very good leaving group. So how are we able to do this reaction if we're not able to kick out bad leaving groups? The reason we're able to do this reaction is because of the small strained ring of the epoxide. The 3-atom ring is very small, very strained, very high energy. So we can kick out an O- leaving group because it actually makes the whole molecule more stable. This intermediate is more stable than the starting material, even though we kick out an O- as a leaving group. If we look at the stereochemistry of this molecule, then I want you to notice that we inverted the stereochemistry at carbon number 5. That fits again with thinking about these reactions as kind of SN2-like processes. The OMe attacks carbon 5, inverting the stereochemistry to put the new group on a wedge. Carbon number 6 never got attacked in this mechanism, so the stereochemistry at carbon number 6 remains the same. This is not the final product. It can't be. We've got this negative charge on oxygen. We don't typically isolate things with charges, so we need to somehow do something to make this molecule into the final product. What we can do is we can throw a hydrogen on that O-, protonate it, add an acid to protonate the molecule to make the oxygen neutral and form our final product. Now, when we do this, any acid will do. There are several that you might see in your course. There are some that I care for that are better, some that I don't really care for. The one that I like to use is ammonium chloride. That's the one I tend to use. So we can use ammonium chloride as our quench in this reaction. I have another video on quenching reactions that I'll link to down below. But the ammonium chloride acts as an acid, the O- acts as a base, and we take the hydrogen from the ammonium chloride to protonate the O- to form our final product. So our final product is the opened epoxide with an OH on the more substituted side and the nucleophile that we added on the less substituted side. We could have used any strong nucleophile, strong base here. This one happened to be methoxide. The methoxide attacks the less substituted side to invert the stereochemistry to open the epoxide under basic conditions.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.